Hey guys, welcome to today's video, which is the first of 3 videos on wave behavior and how that's important to us in chemistry. So you know that Albert Einstein is famous for a lot of things. You may not know that he got the Nobel Prize in Physics for discovering the photoelectric effect. Photoelectric effect is where radiant energy strikes a piece of metal, and in so doing, it dislodges some electrons from the metal atoms, and those dislodged electrons stream along as a current of electricity. That may sound just a little bit familiar to you because in an earlier video, a few days ago, we looked at the workings of the mass spectrometer, and I showed you that at the very beginning of this spectroscopy process, neutral atoms are inserted into the device and then they're bombarded by ionizing radiation. The ionizing radiation dislodged electrons from these neutral atoms, creating cations. So this ionizing radiation in the mass spectrometer is doing a similar thing in this, that the radiant energy is doing with a piece of metal in this photoelectric device. Okay, so we're talking here about radiant energy. Let's define what that is. Radiant energy, also known as electromagnetic radiation, is energy that travels in waves, that's going to be significant, at the speed of light. Now, I know that you know the speed of light is fast. I don't know if you know just how fast it is. 186,282 miles per second. That's crazy fast. Just let that sink in for a minute. Now that number, while it's helpful to us because miles per hour and miles per second is something we can sort of visualize, in our work in chemistry, we're not going to use those units. We're going to use metric system, of course. So these equivalents are saying the same thing. 300 million meters, like a yardstick, 300 million meter sticks per second. Written in scientific notation, it looks like this, or here's yet another more precise version with 4 sigdigs. Okay, so radiant energy is any kind of energy form that travels that fast, and it travels in waves. So let's take a look next at this electromagnetic spectrum, which is simply a visual to help you see some different radiant energy forms that travel at the speed of light and how they compare to each other in terms of wavelength and frequency. Right, so one of the forms of radiant energy that travels at the speed of light is, of course, visible light. So here it is expanded a little bit so you can see the colors of the rainbow that make up visible light. But not only does light travel at the speed of light, so does ultraviolet radiation. This is the kind of radiation that would give you a sunburn. X-rays travel at the speed of light, and so do gamma rays. Gamma rays are a form of radiant energy that are given off spontaneously in some nuclear processes. Heat, better known as infrared radiation, travels at the speed of light. So do microwaves in your microwave oven and even radio waves. So all of these forms of radiant energy have the same speed, but they travel as waves, which mean they have 2 properties that we need to talk further about. One is wavelength. Wavelength is defined as simply the length, physical length from crest to crest. In this spectrum, we're comparing wavelengths in meters, but wavelength could also be measured in centimeters or nanometers or any length unit. This Greek letter lambda is the symbol that we use for wavelength when we use it in equations. Another characteristic of waves is that they have a frequency. Frequency being defined as the number of waves per second. The unit is the per second, and the symbol that we use is the Greek letter nu, which looks like a fancy V. Now on this spectrum, you might be able to see that wavelengths are very short down here. And as we go in this direction, the wavelengths are increasing or getting longer. But the corresponding frequencies that go with each of these are noted here. And notice that the arrow goes in the opposite way. So in comparing frequencies of these, the lower frequencies are here and the higher frequencies down here. So what I'm getting at is that there is an inverse relationship between those two. Let's look at this picture. In the top picture, I'm representing a wave, and I'm showing you here its wavelength, which again is defined as the distance from crest to crest. So here's the crest of a wave and the adjacent wave. Here is its crest, and that physical distance is the wavelength. In my second wave down here, you can see the wavelength is shorter because the waves are closer together. So from crest to crest, this wavelength is shorter than this one. Now let's talk about frequency. We said that frequency was defined as the number of waves per second. So if I say that this line right here represents a second of time, then the frequency is going to be how many wave cycles in that 1 second time interval. Here's a wave cycle, and here's another wave cycle. So this wave has a frequency of 2 waves per second, written simply per second. Now my other wave depicted here that had the shorter wavelength, let's look at the frequency for it. Again, I'm representing 1 second of time here between my two fingers. So in that 1 second of time, 1 wave cycle, 2 wave cycles, 3, and 4. So that's a frequency of 4 waves per second. So again, the inverse relationship as we compare these two waves, the longer wavelength has the shorter frequency. The shorter wavelength has the higher frequency. So in mathematical terms, that inverse relationship can be depicted with this equation. C stands for the speed of light. And we have a relationship that tells us wavelength and frequency inversely related to each other. Well, if you multiply them together, their product is always equal to a constant, and that constant is the speed of light. So let's look at how that would be applied in a problem. What is the frequency of laser radiation with a wavelength 758.0 nanometers? This problem has given me the wavelength, and it's asking me to find the frequency. So I'm going to use my mathematical relationship, my equation that says the product of wavelength times frequency equals the speed of light. Now, they gave me wavelength, and they're asking me to find frequency, so I need to isolate this variable. I'm going to divide both sides of the equation by wavelength, and then I have frequency equals c, the speed of light, divided by wavelength. Now, I'm going to plug in for c, my speed of light. If I look at the number that was given in the problem, can you see that's a 4 sig-dig measurement? This number has a 0 at the end. Sometimes those count and sometimes they don't. But if the number has a decimal, zeros at the end count. This is a 4 sig-dig number. I'm going to use the more precise version for C. So my speed of light is 2.998 times 10 to the 8 meters per second. And I'm going to divide that by my wavelength, 758.0 nanometers. Now, before I grab my calculator, let's just talk units. I have a meter per second in the numerator, and I have a nanometer in the denominator. Meter and nanometer are both length units, but they don't cancel each other out. I need to make use of this little equivalence. Nanometers are very small. There are a billion of these tiny nanometers in a meter stick. 10 to the 9 is a billion. Or you can think of it this way. One teeny, teeny, tiny little nanometer is a billionth of a meter stick. You can use either of those equivalences to build a conversion factor. I'm going to use the top one. So I'm writing down there's a billion nanometers in a meter stick. And of course, I set it up with nanometers on the top so that those units would cancel. And meter in the denominator would cancel this meter in the numerator. All right, now I'm ready to grab my calculator. So I've got numbers in scientific notation. I'm going to multiply all the way across on the numerators, 2.998 times 10 to the 8. You notice I didn't type times 10. My EE button does that for me. Now times, and then my next one is 10 to the 9, which is EE to the 9. That's my numerator. I hit enter, and then divide by to go to my denominator, and I always wrap my denominator in parentheses. 758.0 times 1, close the parentheses, and hit equal. So the correct answer here is 3.955. I'm going out to 4 sigdigs. Look all the way out to the end of your display. There's E14. So this answer is 3.955 times 10 to the 14. And my unit, again, meters canceled, nanometers canceled. And here's my unit of per second, which is exactly the appropriate unit when solving for frequency. Okay, let's do one more. Example 2, what's the wavelength of radiation with a frequency of 1.78 times 10 to the 18 per second? Okay, they have given me the frequency, and they're saying what is the wavelength? So that's what I'm solving for. My math relationship says that the product of those two is equal to the speed of light. Okay, I am trying to solve for wavelength, so I want to divide both sides of the equation by frequency. And my equation now looks like wavelength equals speed of light constant divided by frequency. Okay, this time my frequency has 3 sigdigs, so I'm going to use this version of the speed of light, although guys, it would never be wrong to use the more precise version. Okay, 3.00 times 10 to the 8 meters per second, and I'm dividing by a frequency of 1.78 times 10 to the 18 per second. Per seconds divide out. And you can see this is going to give me an answer for wavelength in meters. So common sense check, that's totally appropriate. Let's just suppose though that they asked for the wavelength in angstroms. So now I need to make use of this equivalence. Angstroms are even smaller than nanometers. It takes 10 to the 10 angstroms to equal a meter stick. Or one teeny tiny little angstrom is equal to 10 to the minus 10 meters. I'm going to use that equivalence in this problem. So I will have 1 angstrom in the numerator and 10 to the minus 10 meters in the denominator. This unit meter is going to divide out, and I'll be left with the unit angstrom. All right, grab your calculator. So we're going to go all the way across on the numerator, 3.00 times 10 to the 8 times 1. Okay, you can choose to do that or not. Equals. Okay, there is my numerator. Divide by, and I always put my denominator in parentheses, 1.78 times 10 to the 18 times 10 to the minus 10 is EE minus 10. Close the parentheses and hit enter. And my wavelength, this time I'm working with 3 sig digs, so I'm going to call this 1.69. Scanning out to the side, there is no exponent. So 1.69 angstroms is my wavelength. All right, so guys, I hope those 2 examples helped you to see how we're going to apply this equation, solving either for wavelength or frequency. And along the way, chances are good that you're going to need to use these equivalences. So you're going to want to put them in your notes and start getting really familiar with them. And then the last thing I want to point out is this relationship that we've discovered, which tells us that when wavelength is long, frequency will be low, and when wavelength is short, frequency will be high. All right, guys, I hope that was helpful.